Hi everyone, and welcome to a new video about control system topics, and we continue with the subject of stability. And in this example we will look at Nyquist plot and stability, and we will see how we can determine the stability of a system with a time delay. Now, as we did in the previous examples, we will look at the calculations in this exercise and also the simulation results to verify our calculations. So let's look at the exercise, and this is our example number 1. Okay, now we have the following situation. We have the plant here, which is given by g of s, which is in cascade with a gain, which is now a proportional controller. Now the transfer function of the plant is shown here. As you can see, it is a first order system with a time delay, and a time delay is just given with a exponential function, and the time delay is 0.6 seconds, as you can show here. Now the controller is just a k, so which is just a proportional controller. Now the question in place is the following: calculate the range of the controller gain k to have a stable closed-loop system. Now use Nyquist stability criterion. Okay, so the first step in the analysis is determine the loop gain L of s of this system. Now the loop gain is just the complete loop transfer function of this system. So you start at one point and you make the full circle and you come at the same point here in this case. So if I now do the analysis for the loop gain, L of s is actually k times gs. Now k times gs, which is actually shown here. Okay, now this is just an expression given in the s domain. Now to analyze the situation in the frequency domain, I have to convert the s domain representation of the loop transfer function into the j omega domain. So that's actually the next step, step 2. So let's do that. Just replace everywhere where you see a s by j omega, as you can see here, which is also shown here. Now I have purposely made the gain in red and the plant in blue, as you can show here. Now if I now follow the situation in the next step, I have to convert the e to the power minus j 0.6 omega using Euler's formula. That will be helpful in the further analysis. So if I now rewrite this in this form, as you can show here, which is now given by the cosine and the sine expressions. This is a very familiar expression. If I now substitute this expression in here, I get the expression for the loop gain as follows. Now in the next step, what I want to do is I want the denominator expression of the loop gain as a real value, because this is a complex expression which has an imaginary and a real part, but I would like to get rid of this imaginary part also. So what I do is I will multiply the numerator and the denominator of this expression by the complex conjugate of this expression. So what I do is the next one. So I multiply this by minus j omega plus 4, which is shown here, and I do it also with a numerator. Now if I now work out the expression here, I will get in the next step omega squared plus 4 squared. So this is pure real value. Now in the numerator I have still this expression of minus j omega plus 4, and this expression, which is now from the time delay expression of the e to the power minus j 0.6 omega, is still there in place. Now the next step here is actually rewriting this parentheses and this parentheses such that you have just one real value and one imaginary value. So we have the one real part and the one imaginary part collected together. So it's actually done here in the next step. Now the 4k divided by omega squared plus 4 squared, which is just a vector, which is actually placed in front. Now if I work out the parentheses here, I will have 4 terms, and I have collected also the imaginary parts and the real parts together. So this is the real part and that is the imaginary part. Now, if I work this further, I can now collect this imaginary part in a nicer way, which is now shown here in this expression. Okay, now the next step, step 3, is determine the critical frequency, omega critical, for stability. So the situation is for, in this case with the Nyquist stability criterion, is we look at the situation where the loop gain is exactly 1 when the phase shift is minus 180 degrees. That's the condition of Nyquist stability criterion. So what I want to do is first look at the situation where I see in my Nyquist plot the -1 point. That is really interesting because the loop transfer function will make a Nyquist plot as shown here. The length from this origin to this line, to this plot, is actually the magnitude of my loop gain, loop transfer function, and the phase for each point here, determined actually by the position of this line, is the phase corresponding to the frequency here. So if I want the phase shift of minus 180 degrees, I have to make a full half circle here, and I have to come actually at this point. So this is actually the dot for minus 180 degrees, and that will give me the critical frequency. So what I do is, in analytical form, I have to make the imaginary part, because this is imaginary and the real part, I have to make the imaginary part 0. So that means set the imaginary part of your loop gain equal to 0. Now in this case, this is the real part and this is the imaginary part. So if I make this expression, only this expression, 0, I have actually determined this point. So let's do that. Just omega times the cosine of 0.6 omega plus 4 times sine of 0.6 omega is equal to 0. Now, if you calculate this, just work it out. You just place this to the right side, just from the sine, just a little bit easier to follow, and then make the omega is equal to minus 4 sine 0.6 omega divided by the cosine of 0.6 omega. Now, you can of course simplify this, or I mean rewrite it in a different form, minus 4 tangent of 0.6 omega. That's actually the omega is equal to minus 4 tangent of 0.6 omega. Now you can now solve this using a calculator or another form using a program. Now if you do that, you will find a couple of values. Now we will take the smallest positive omega, and that will be in this case 3.94 radians per second. And this is our omega critical. So we have now defined our omega critical, we have found, which is in this case 3.94. Okay, now this will be used in the next step. So we will now substitute this value of 3.94 into the loop gain expression, which is now this, just L of omega, j omega, we have determined previously. Now we have now the following situation. If I now just substitute this in the expression, I have now the following. Just follow actually what I have in blue, and this is actually substituted in the expression of the loop gain. Now, when I calculated the loop gain phase difference of minus 180 degrees, I have made the imaginary part equal to 0. And what I also want is, I want to have the magnitude of that loop transfer function equal to 1, such that I can determine how far I can go with my gain. So the next step is, let me also emphasize this, this is now the real part, which is just calculate this minus 5.61, and if I now calculate also this one, which will be 0. This is of course not a surprise, because we made the imaginary part equal to 0, and this was the result of omega, and that is actually, in this case, if you substitute the value, you will get the 0. Now, if I now work out this, I will have the following expression, just simplified form. So that is 3.94 squared plus 16, which is this 31.52, and we have 4k divided by that exact same number, and then we have minus 5.61 plus j0. Now this is just pure real expression. Now if I now work it out, I will get the loop transfer function at the critical frequency is minus 0.712k. Now, as I said before, this expression must be set equal to 1 in order to calculate a critical gain, because that determines the maximum allowed value for your proportional controller gain k in order to stay in the stable region. So you may have a stable closed system. So if I do this, we set the value of the loop gain at the critical frequency equal to minus 1. That means actually this value, or this, must be set to minus 1. Now, this is now set to minus 1, which is just minus 0.712k is minus 1. Now, if you work out here the math, you will get 1.404 as the value for k, which is now defined as k critical. Now, the conclusion is the following. If you make your value of the proportional controller k larger than this value, so if k is larger than 1.404, the loop gain will encircle the minus 1,0 point. So that's actually the important point for our stability analysis using Nyquist stability criterion. And that system will be unstable. So you want to stay away actually from that minus 1,0. So this point is interesting. Now, in addition, the controller gain also must be positive. That means if I make the k smaller than this number, so 1.404, but larger than 0, that will make the system, in this case, stable. So in order to have a stable closed system, we require k must be larger than 0, but smaller than 1.404. Now this is for this exercise in the calculations. Now let's verify also our calculations using the simulation results. So that's actually our next step. Now, the simulation results, let's start first with a Bode plot of the loop gain with a controller gain of 1. That means actually just you have a controller, but the gain is just 1. Actually, there is no controller. There is no additional action in place. So let's look at the situation for this case. Now, this is the Bode diagram or the Bode plot of the loop gain with a controller gain k of 1. Now, I've set this equal to L. What you can see here is the following. If I look at the phase plot here, and if I look at the minus 180 degrees, I see that indeed the frequency is 3.94 radians per second, which is the critical frequency we have calculated. We also see at this same frequency, so if I go to the magnitude plot for the gain, is if I look at the same frequency, I see a magnitude of minus 2.95 dBs. It is a minus, that means actually the following. At this frequency, I have a phase shift of minus 180 degrees, but the gain is minus 2.95 dBs. So in order to have an unstable system or at the edge of the stability, I must have at minus 180 degrees a magnitude of 0 dB. So if I stay away from the 0 dB, which is actually at this part, I have a headroom of this much gain. So that means actually the following. Again, looking at this and this two labels, if I look at the situation here, I have a allowed loop gain of 2.94 dBs. Now, if I of course work it out and rewrite this in a different form, because it's just in dBs, another unit, that will result in 1.404, which is actually calculated. So I can add a loop gain of 1.404 in this system to come at the edge of stability. That's actually the conclusion from this Bode plot. And again, you see that the critical frequency is 3.94. Again, that will confirm our calculations. Now, if I look at the situation, the result in the Nyquist plot, again with a gain of 1 for the controller, I have the following situation, which you can see here. This is the blue curve. I have a gain margin, as you can see here, is 2.94 dBs. Again, very close to what we have just determined from the Bode plot. And it happens exactly at the same frequency at 3.94 radians per second. And the system is stable in this case. Now, if I look at another label I made here at the exact same point, you see that the real part here is minus 0.71. And imaginary part is almost 0. So I've actually chosen this point such that the real imaginary part is almost 0, which is actually what we did in the analysis. We made the imaginary part of our loop transfer function 0 and then determined the maximum allowed controller gain. So this gain, this actually the distance from the origin all the way here is 0.71. Of course, there's a minus sign because we are now at the left side. Now, I have a room till the -1 point, actually from this point to that point, and that value is actually how much gain you can add until you get unstable or at the edge of the stability. So this is actually the unit circle. So if I now look again for this label, what you see is that the gain margin is 2.94 dB, so allowed loop gain is again 2.94 dB, which is very close to what we had also in the Bode diagram, and the real value is minus 0.71. That means you have 1 over 0.71, which is approximately 1.408, which is very close to 1.404 as the gain for the loop gain. So we see that the Nyquist plot and the Bode diagram give actually a similar result for this analysis. Now, if I look at the Bode plot of the loop gain with the controller gain of exactly 1.404, just a Bode plot, I have then the following situation. Now, this is now denoted as L critical. Now, if I look at the phase of minus 180 degrees, I see again the critical frequency of 3.94. But at the same frequency, I see that the magnitude is almost 0, which is the effect of gain of 1.404. So I see that the edge of instability is shown here in this label. So that means allowed loop gain is almost 0 dB. So I cannot add any gain in this system. That means you cannot go above this value for your controller. So this is the maximum value of the controller gain. Again, that means edge of stability. Now, if I do the same situation for the Nyquist plot, again, now the controller gain is set to 1.404. Then you can see the phase margin is very close to 0, so there is actually no headroom for any stability. Delay margin is also very close to 0, and at the same frequency, at the exact same frequency as we have calculated here, you can show here that the 3.94 radians per second. Is the closed-loop system stable? It says no. So it means actually the situation is here clearly unstable at the edge. And for another label, I have also checked that I placed the cursor such that the imaginary value is almost 0. I see the real value is almost -1. Now again, the same frequency is shown here. So phase margin almost 0, that means edge of stability, and we have real values almost -1. That means there is no room for additional loop gain in this case, with a controller gain of K is equal to 1.404. and you can see the closed-loop system is not stable. Okay, that's actually for this part. Let's look at the step response also. So we have also the step response for this circuit. Let's look at the situation where we have the controller gain of 1. So what you see is the following. Now we see a huge overshoot. The rise time is 0.137 seconds, but the overshoot is almost 83%, which is a lot. Now there is also a settling time of 9.4 seconds. Now that means actually this system is of course stable, but it is of course having a large overshoot. So large overshoot, and the settling time is also quite large, but it is still stable. So it is not a problem in terms of stability. Now if I look at the situation where the gain goes to 1.404, and again you look at the unit step response, I see at that value for my controller gain that the unit step response shows actually an oscillation. So that means actually we see an oscillation. That means this is the edge of stability, and this is now also the confirmation using a unit step response. So we have actually looked at different ways to confirm our calculations. We have looked at the Bode plot, we have looked at the Nyquist plot, and we have also made the time response to the unit step response, and we have actually concluded that the K value, the controller value of 1.404 is actually the maximum value that you can have in this system. So let's also look at the situation where we compare the time delay and without a time delay. So we have a system with a time delay, a system without a time delay. Now if I now look at the Nyquist diagram specifically, what you see is the blue line, which is the first order system without a delay, and the orange line, which will circle all the way to the origin and keep circling. This is actually a system with a delay. So we have a first order system that stays always stable. Whatever you do with your gain, it will never encircle this -1,0. That point is the critical point actually for stability. But if you look at the orange line, you can have an encirclement of this -1 point if you make your gain larger. So the conclusion here in this exercise is, if you have a first order system, that is not always per definition stable whatever you do with your gain. If you have a delay in cascade, in combination with your first order system, you need to be careful with your controller gain, because that can cause an encirclement of this -1 point and make your stable unstable. I hope this exercise have clarified this situation in more detail, where we have a time delay, which is a very important topic. We will continue with other exercises. I will also make the example using a second order system, and also where we have a different analysis. And also will produce another example where we see how we can determine the maximum allowed delay in our system. So that will be in our next examples. So keep in touch, and if you have any questions or comments, please let me know. Thank you very much, and see you next time.